Alright, today's lesson, we're starting to get into it a little bit more, so is Ohm's Law. So on the there's a video, Ohm's Law there on the website, you can click on and you can have a look. So what Ohm's did is, Ohm I should say, not Ohm's, what Ohm did is he looked at different circuit elements and things, and what he was interested in was voltage and current. So if you changed the voltage on something and the current, how that all changed and what happened. So what he did was he did a number of things, and some of them came out to be a straight line like that. And so what we could say from that is that as the current increases, then so does the voltage increases as well. So from this we can say then that the voltage is proportional to the current. Now, in mathematics, what you know about proportionality is that you can replace that by equaling some constant, and in this case, for Ohm's law, and we also know from mathematics y equals mx plus c, that constant would be the gradient. So in this particular case, for Ohm's law, or things that are ohmic, i.e. a graph of volts versus current is a straight line, you can say V equals IR. And this R here is the gradient of that line. Alright, so in your notes there, underneath that V equals VI graph, you can see it says that it is said that the element obeys Ohm's law. So anything where we get a straight line, like this one here, obeys Ohm's law, and then V is proportional to I, and V equals IR. Alright, now the other thing about this R here is that it's what's called the resistance, and it's measured in ohms, which is capital sigma, and it's the symbol rather than having to write out the word ohms. Alright, so that's what that is. So what is Ohm's law? Ohm's law is this thing here, V equals IR. Alright, and so as we would know, this R, because it's related to the gradient, it's the resistance. The bigger the resistance, the steeper that line would be. Alright, so in your notes there you've got an example. So here's our example, a resistor of 5 ohms is supplied with a potential which can vary from 1 to 100 volts. So the question says, what will be the range of the current that will flow in it? Alright, so for part A, V equals IR connects the resistance, the voltage and the current together. So because we're after the current. Alright, so when V equals 1 equals the current times 5, so the current there is 1/5. Now in physics we don't like using fractions, so you need to say 0.2 of an amp. Now the other end of the spectrum, of course, is when the voltage is equal to 100, then 100 equals I times 5, and dividing both sides by 5, you get 20 amps, which of course is 100 times the original answer. Alright, so that's part A. Part B says how much energy would be dissipated. Alright, so energy, electrical energy, there's a few different ones, remember. There's VIT and there's QV. Alright, so then it says each second. So dissipated each second. So what have we got? Well, we've got time. 1 if it's each second. We've got voltage. And we figured out down in part A, current. So, what we're going to do then is say that the 100 times the current, which is 20, times the time, which is 1 second, and so the energy that's dissipated is 2000. Because it's energy, it's measured in joule. Alright, now in the next bit of your notes, there's these diagrams. Alright, now the graphs have just been flipped around, but that doesn't, so instead of having V on the vertical and I on the horizontal, they're flipped around, but it doesn't actually make any difference. The one in the middle, because they're still graphs of voltage and current. The graph in the middle, this one right here, we notice that's a straight line, so this thing that's called a resistor, which is just something that resists current, simple as that. That one here obeys Ohm's law, so that would be what we would call ohmic. Now some of them don't have straight lines, so the one, the light bulb for example, you can see that that's got a curve. The diode also see that that's got a curve. So these two would be called non-ohmic. Alright, so things like the one in the middle are ohmic, and the ones with the curves are non-ohmic. So when we've got non-ohmic devices, we need to use the graphs to find some information. Alright, so here's how we would do that. So in your notes, we've got another example. Alright, so here is our example. And it says the graph represents the IV or the VI characteristic of a 240 volt 60 watt light bulb. So we've got some information here. We've got voltage, and here we've got power. Alright, so that's what it's rated to anyway. It may not necessarily be operating it optimally at that, but that's what it's rated to. Okay, so what is the resistance at 24 volts? Okay, so 24 volts, what we need to do is we need to use the graph. So at 24 volts, which is about there somewhere, we would need to go up till we hit there, and then we come across. So at 24 volts, and so I'll do that over here, number A, so V equals 24. The current at that time looks like it's 100 milliamps, 10 to the minus 3. So we can use that to help us. Alright, so if we do V equals IR, even though it's not ohmic, we can use that at that point. When we move on to parts B and C, we'll need to make some adjustment, and we'll get to that. So 24 would be 100 by 10 to the minus 3 by the resistance, and then if you divide by 100 by 10 to the minus 3, you will get that the resistance at that time is 240 ohms. Alright, so just as an aside, the thing we know about light bulbs is the wire in them, when you put current through it, heats up, and the resistance changes when it heats up. Alright, the next one, we would need to then do a similar thing. So at 120, so at 120 is about there somewhere. We go up and across here, and across here, and there it's at 200 milliamps. So when V equals 120, the current equals 200, 10 to the minus 3. And so 120 equals 200 by 10 to the minus 3 times the resistance, and then when we divide both sides by 200 by 10 to the minus 3, we'll get 600 ohms. Alright, so as I said before, as you put current through it, it heats up, and so now the resistance changes. So it's now got a higher resistance. Alright, part C then. We need, so 240, where's 240? 240's about right on the end of it, right there. And then we go across here, and it's that number that's there. So that's 2 boxes above, and between 0 and 100 there's 4 boxes, so each box is 25. So 2 is 50, so that's 250 milliamps there. So voltage at 240, the current is 250 by 10 to the minus 3. Remember, milli, 10 to the minus 3. Just to highlight that, milli by 10 to the minus 3. Putting those numbers in to V equals IR, 240 equals 250, not 2. Let me rub that out. Glad I found that error. There we go. 250 by 10 to the minus 3. That minus in there we are. So 250 by 10 to the minus 3. And times by the resistance, and when you get that, the resistance would be 960 ohms. Alright, so more current's heated up more, and resistance has increased. So I've squeezed that in there a little bit. It's in your notes. I've used a slightly different method in your notes, so if you're confused about what I've done, make sure you ask. Alright, yeah, sorry, I squeezed it in because I didn't want to go back to 40 pages, but maybe I should have. Alright, anyway, that's a aside. Alright, the last bit in your notes talks about resistances. So resistances are anything that resist flow of electrons. Alright. And the bigger the number, the more resistance, which makes higher resistance. Now, experiments, and we don't need to know this in great detail, but experiments show that the resistance depends on a few different things, and so you just need to to know qualitatively, not quantitatively. Depends on, firstly, the length of the wire, of the thing. Secondly, the cross-sectional area. And thirdly, this thing called, which depends on material, and it's called resistivity. So that's the length. So if it's a wire or something, the length, that's your cross-sectional area. And then this thing relates to the material resistivity, it's called. Alright, so things like copper and gold have a low resistivity, and other metals and other things, glass for example, has a very high resistivity. Alright, so that's all you really need to know about resistances. Depends on the length, cross-section area, and the material. Alright, so then there's some questions in your textbook. Don't forget, if there's anything in this presentation that you're not sure of, make sure you ask.